I have come up with some more questions today from the coordination chemistry chapter. Okay, so this is the first question for today. Arrange the following metal complexes in order of their increasing hydration energy. Okay, this hydration energy, lattice energy, spinels, they are applications of CFSC. Okay, so okay, these are the complexes that are given to us. All of them are in the +2 oxidation state, as you can see here. Okay. So when 1 mole of an ionic crystal is dissolved in water, the water molecules are gathered around the ions and the energy is released, which is called hydration energy. Okay. So this is the definition. Now, you can see that hydration energy is directly proportional to charge and it is inversely proportional to size. Okay. So now this is important. You can see hydration energy experimental is equal to hydration energy theoretical or calculated plus CFSC. Okay. You can read it this year. Read it. When a dipositive metal cation of 3D series, all of these belong to Mn2 plus, vanadium 2 plus, nickel 2 plus, and titanium 2 plus. All of them belong to 3D series. Transition metal gets hydrated. A high spin octahedral aqua complex is formed. There, okay, a high spin. Now you can see high spin, low spin. So for that reason, therefore, not only the hydration energy but also CFSC. Oh, where is it? Yeah. CFSC is involved. So this is the answer. We will discuss in the next slide. Yeah. Okay. So this graph here you can see that this dotted line, this one, the lower one, this comprises of hydration energy without the CFSC. Okay. And this hump, which you can see two humps are there, right? These belong to the hydration energy with CFSC. So for talking about cadmium, manganese 2 plus and zinc 2 plus, you know that the CFSC is 0, right? For calcium, it doesn't belong to the 3D series. And manganese 2 plus 3D5 4s2 CFSC 0 because it will be 3D5, and for the zinc 2 plus it will be 3D10, again the CFSC will be 0. So the hydration energy, the experimental hydration energy becomes equal to the theoretical hydration energy for the three ions: calcium 2 plus, manganese 2 plus, and zinc 2 plus, as the CFSC is 0 for all for the three of them. Okay, so that you have seen. Now talking about these are the CFSCs that I've written for these +2 dipositive ions. D1 it has minus zero point 0.4 del naught. You can see. Now here you can this is scandium D1, titanium, vanadium. Scandium, titanium, vanadium. The third one is vanadium. We have 3D3. If the configuration is 4s2 3D3, two electrons have been removed, so we get 3D3. The CFSC is minus 1.2 del. And same, it is the same for the D8, that is nickel. 4s2 3D8, two electrons have gone, so 3D8, so minus 1. So how will you differentiate? On the basis of size. You can see here that hydration energy is inversely proportional to the size. Smaller the size, greater will be the hydration energy. So that is why this nickel complex has the highest hydration energy, right? R. Then next to that is Q, this vanadium. Oh, sorry. Yeah. So talking about vanadium, so next one is vanadium. Nickel, vanadium, E is manganese, and titanium. Okay. So if we want to differentiate between vanadium and manganese, we will see that the CFSC, here you can see in the graph that for the manganese, the CFSC is 0, and therefore the hydration energy experimental and theoretical, they are same. They are lying on this dotted line itself, right? But but the hydration energy of vanadium is higher as compared to manganese. Why? Again, we can see that on the basis of size, we can see, right? Left to right, size is decreasing. Here you can see this is R for the nickel complex, Q is for the vanadium complex, right? Then it is manganese, and then coming on to titanium, right? I'll just show you again. Okay. So D3 is minus 1.2, and that I've shown to you. Okay. So talking about this trend, the titanium and manganese, right? Titanium and manganese, Sp, if we see, titanium has lesser hydration energy than manganese, even though the CFSC of manganese is zero, but the hydration energy is higher. Why? Because of the size. Left to right size is decreasing. Manganese has a smaller size. Mn2 plus is smaller than titanium 2 plus. That is why. Okay. And now if you want to okay. Now for the vanadium, you can see the experimental hydration energy is higher than the manganese one because it involves CFSC as well, right? For the vanadium, minus 1.2, and for D5 manganese, it is 0, right? Here CFSC is also involved, so therefore the hydration energy is higher. Experimental hydration energy is higher than the manganese. Okay, so like this you can uh, like this on the basis of two you can compare at a time. You can compare two, like I compared manganese and titanium, S and P. Then you can compare between this nickel and vanadium, how they are differentiated on the, and then you can arrange the whole like in the increasing or decreasing order, whichever order it is given. Okay, so our highest will be for the nickel, this one. Then it will be for the uh, vanadium, and then for the manganese you can see here, and the last will be for titanium, right? So on the basis of size you can compare when the CFSC is same, here minus 1.2 del 1 minus 1.2 del. Okay, so this one is done, this question. Yeah. This is important. You have to see Orgel diagram is important, and th- this is for the this is a like a P6. Okay. Okay, we'll continue. The number of absorption bands observed for FeF63 minus and COF63 minus respectively are. Okay. So iron is in the +3 oxidation state. You can see it, Fe3 plus. So it has 4s2, 3d6, 3 electrons have been removed. We get a configuration of 3d5. Okay, this is just a brief I've given to understand this question. Orgel diagrams are applicable only for spin-allowed transitions. Only for spin-allowed. Also only applicable for high spin octahedral and tetrahedral. Both of them are high spin as the ligand is fluoride, F minus, weak field ligand. And what is the plot? On the y-axis, we get energy, spectroscopic terms versus ligand field strength. This is on the x-axis, right? Ligand field strength. Okay, Mulliken symbols. T is for the triply degenerate, E is for doubly degenerate, and A is non-degenerate. Now these answer I'll show you. Yeah. Okay. So this is the Orgel diagram for D6 high spin octahedral. Now, how do you get this minus zero point 0.4? You know that, right? Minus zero point 0.4 into 4 will be minus 1.6 plus zero point 0.6 into 2, 1.2. That is minus 1.6 plus 1.2, we will get minus zero point 0.4 del, right? This is the CFSC, this gap, basically, right? Del. This is your del. And similarly here, zero point 0.6 del, how you've got it? T2G3, 3 into minus zero point 0.4 plus 0.6 into again 3. So you get zero point 0.6 del. Okay. So this ground state term. Ground state term for this configuration D6 is 5D. How do you get 5D? I'll show you here. How do you get 5D? Okay. Okay. So this is your 5D orbitals are present, right? So you'll fill the electrons here. 1, 2, 3, 4, and 5. Okay. And the sixth one also here, right? So for calculating the term, how do we do it? Plus 2. I had shown you in the first class for one of the ions. I had shown you how do you calculate the term and the term symbol. So minus 1 and minus 2, right? Okay. So what is this D? How do you get D? I'll show you. D is basically the L, total orbital angular momentum. So I'll not write it. I'll just tell you how to do it. Okay. So plus two for this, these two electrons, plus two, and then plus one for this one, 0 for this one, minus 1 for this one, minus 2 for this one, right? So you can cancel out minus 2 and plus 2. 1 plus 2 will get cancelled from here. Plus 1 plus minus 1 will get cancelled. So what we are left with? Only 2, right? Plus 2. 2. So for that, the term is, what is the term? The term is D, right? Okay. And how do we get 5? Because there are 4 unpaired electrons. So S, the spin angular momentum will become, it will be half plus half plus half plus half. That will be 2, right? So the spin multiplicity is 2s plus 1. So 2 into 2 plus 1 will be 5, right? So that is how you get this 5D ground state term. Now for this ground state term D, T2G and EG are there. You have to like, you should know this. For D, like for the F, it was T1G, T2G, and A2G, right? Similarly, for D, we have T2G and EG, and this 5 will be the spin multiplicity. Okay. So now this is what I told you in the previous slide. The energy, the spectroscopic term versus the ligand field strength is plotted here. The weak field or the strong field. Okay. So this has lower energy, minus zero point 0.4 del U. This will be lower side, and 5 Eg, that is zero point 0.6 del U. So yeah, how do we get Eg? E. That is, I mentioned this here. Mulliken symbol. T is for triply degenerate, E is for doubly degenerate. This is triply degenerate as the T2G orbital is unsymmetrically filled, and here the EEG orbital, this upper one, it is unsymmetrically filled. That is why we get E, and here we get T. Okay. Yeah. So now you can see that only one transition is possible from here to here, from lower state to higher state. Only one transition is possible. This will be your del. Okay. From 5T2G to 5EG. Yeah. Okay. The other complex that is given to us is FeF6 3 minus, right? That is your D5, right? D5 for octahedral or tetrahedral, it will be the same. Now D5 you'll show like this. D5 on giving energy, you'll one electron will move to the higher state. Now it has to change its spin to go to this state, right? You have to change the spin. Now here the spin was 5 by 2, one half into 5, right? And here it is 3 by 2. As the spin has changed, You can see that Orgel diagrams are applicable only for spin allowed transitions. Here the spin has changed 5 by 2 to 3 by 2. So delta S is not equal to 0. 3 by 2 minus 5 by 2 will not be equal to 0. So this is spin forbidden, right? Spin forbidden. So no peak will be observed for the D5, octahedral or tetrahedral. 8. Okay, so the number of absorption bands observed for this D5 and this one is your D6 respectively are 0 and 1. Okay, no peak for the first one and one peak for the second one. So it is very important that you do the Orgel diagrams for every for every configuration. You should know. Okay, for the D2, D7, D3, all of them you should know it. Okay, how the transitions are taking place and how do we calculate the del low. So questions are asked that from where to where the transition will take place, as questions are asked like from a 5T to G2, 5EG, which will be the configuration, or the configuration is given to you and you have to tell from where to where the absorption bands are seen. Okay, so this is important, Orgel diagram. As Sugano diagram is also there, but that is not very important. Questions are not very frequent from there. Okay. So anyway, we will move to the next question. Everything is done from here. Yes. Okay. Yeah. So diatomic term symbol. This is also important. Like you have seen term symbols for the configurations D5, D6, and like any of them D2. The term symbols, you know how to derive them. I showed you in like in yesterday, in day before yesterday's class, right? So arrange the following diatomic term symbols for O2. So this is diatomic term symbol. This all these are three term symbols that are given to us. They belong to O2 in the increasing order of their energy. Three term symbols are given to us: first, second, and third. So we have to arrange them in the increasing order of their energy. And in this question itself, I'll tell you how to derive these term symbols, because questions are also asked from here that how you derive the term symbol for O2, for H2, or for NO it can be NO also, because it might have center of symmetry, it might not have center of symmetry. Okay, so in that case, you have to know, you should know it. So this is the molecular orbital diagram for O2. This I've shown here. Actually, it's not very neat, but yeah, still you can understand. It's understandable, but okay. So this is for O2. It is there. So it will here also. Here it will be O, and here also it will be O, right? So now one is the combination. You know that bonding and anti-bonding orbitals, right? So this is bonding, anti-bonding, sigma U, sigma G. Then again bonding. This is anti-bonding, sigma star 2s or sigma U. Here it is sigma 2pz or sigma G. It has a Gired character having a center of symmetry, and pi U. Now in the case of pi U, I have to see that pi U is, it is bonding. It has a bonding character, while pi G has anti-bonding character, right? For the case of oxygen. Now, and what is the HOMO here? HOMO is this one only, where two electrons are filled, pi G and pi G, right? This is your basically 2px and 2py. Sigma star, sorry, pi star 2px, pi star 2py. Or you can call it pi G also, pi G, right? So you have one electron each in these, right? So this will be the HOMO and this will also be the LUMO. Why? Because two more electrons can be filled here, right? So this will be the LUMO aspect. So, okay. So it was not required here, the molecular orbital diagram was not, but yeah, in order to understand, you should know from where pi G has, from where these two electrons have come. Like we require it in the next part. subsequent slides. Okay. So yeah, how do you derive this? A molecular configuration is a specification of the occupied molecular orbitals in a molecule. Okay. A given configuration may have several different states depending upon how the electrons are arranged in the valence orbitals. A molecular term symbol labels these states and specifies the total spin and orbital angular momentum of the molecule along with various other symmetries. The term symbols are of the form this. Okay, so this is that you do for the determining the term symbol for D2 or D3. You do it like this. This is L. You put N, and here it is your spin multiplicity 2s plus 1, right, and J, right. So there we use L, and here we use this symbol, and they are the same. Right, okay, orbital angular momentum. So S is the total spin angular momentum quantum number, and this symbol is the quantum number for the total orbital angular momentum of the electrons about the internuclear axis. For all the sigma orbitals, the symbol is 0, right? I'll show you. You'll understand it when you solve one of the for the term symbols, right? So the possible values of this can be 0, 1, 2, 3. So each numerical value of corresponds to a Greek letter: sigma, pi, delta, and phi. You have 0, 1, 2, 3. Like for the value of L, for the S, you have 0 here when you determine the term symbol for the configuration. It's going to be L is 0, then you have the S term, L is 1, you have P term, L is 2, you have D term. Similarly, here you have these symbols: sigma, pi, delta, and phi. Okay, 0, 1, 2, 3. They have these values. Okay. So GU subscript applies only to molecules with a center of symmetry. O2 has center of symmetry, so G and U will be applied here. NO doesn't have a center of symmetry, so GU will not be applied there. So for homonuclear diatomic molecules, like for example O2, there is inversion symmetry. This can be thought of as a simple multiplication of functions of even or odd symmetry. Thus, for a pair of electrons in the same sigma G molecular orbital, the product would be Girid into Girid, which is even into even, is equal to even. Thus, the symmetry is Girid. So, in general, you have to remember this. This theory you need not remember. You have to remember the pointers. This one, this pointer. Okay. The theory I've just written for understanding a little bit. You have to remember these things, that G into U is U into U is G into G is G. Okay. And here also you have to remember this only. You don't have to learn all these things. You have to remember a few things only, right? This you should know, that how it is written. Similarly, these symbols. Okay. Now in this you have to, all these pointers you have to remember. The plus minus, if the MO is this, and this is also important. See homo. So the plus minus superscript applies only to sigma states. If MO is sigma, molecular orbital is sigma, then always plus. If MO is pi, then 2s plus 1 will be plus, and 2s plus 1 is equal to 3 will be minus. Now you will not be understanding what I'm saying here. After solving one of the questions, you'll understand. Yeah. So in the question, we have been given with these terms. So I'm showing you how these terms have come, term symbols, right? How they have come up. I'm just showing you for your understanding. Although it is not required in this question, but you should know it because such questions are also asked, deriving the term symbol, right? Yeah. Okay. So for the O2, you can see here now pi g and pi g. I showed you there pi g 2px, 2py, pi 2px, pi star 2px, pi star 2py. This one, right? Each has one electron. Now, there can be different ways of filling those one electron, right? If you fill in 2px, now, yeah, you can see this first. You can see this. You know this, in fact. O2 has 2p, right? The outermost orbital, 2p4. So n is 2. The principal quantum number is 2. Then L is your azimuthal quantum number. It is 0 to n minus 1. I'm just showing you 0 to 2 minus 1, 0 to 1. So M, magnetic quantum number, minus L to L, minus 1, 0, plus 1. 0 is for the PZ, yeah, and minus 1 and plus 1. It can be for PX or PY, like minus 1 can be for PX or PY. Like it is not defined. That is not defined, yeah. Okay, so anyway, we'll come up here, yeah. So ML here will be pi star 2px is present. So L values will be, it will be plus 1 and minus 1 here. 2px will have plus or 2py will have plus. Then the other one will have minus, right? Okay. So L, if you want to calculate L, the capital L, orbital angular momentum, plus 1 minus 1, that will be 0. Spin, spin angular momentum, that will be half plus half, it will be 1. So 2s plus 1, spin multiplicity, 2 into 1 plus 1 will be 3, right? So you get the sigma term. How this sigma? Because I showed you that, you know this. Yeah. So for the sigma term, we have for 0, we have sigma term, the first one, right? So this is sigma, 3 is your spin multiplicity, G is, yeah. So where do you get G? From where do you get G? Here you can see G into G is G, right? G into G is G. Here both of them are G. G into G will be G. And minus, how do you get this minus? Because 2s plus 1 is 3, right? That is why you're getting minus. And it is present in the pi orbital, right? Here it is mentioned. Yeah, if the molecular orbital is pi, then 2s plus 1 is equal to 3 will be minus. That is why minus. Okay. Now on the second one, you can see pi g, if both the electrons are filled over here together, so Ml will be plus 1, minus 1. This we don't need, minus 1, plus 1, plus 1. Both the electrons will have 1, 1. Or the orbital angular momentum will be plus 1 is equal to 2, right? And S will be plus half minus half is equal to 0 because both are present in the same orbital. 2 into 0 plus 1 will be 1. Now L is 2, so sigma pi delta pi. Sigma pi delta 2. 2 delta, right? So delta 1 is your spin multiplicity 1. G is again this. I'm talking about this orbital where 2 electrons are present. G into G will be again G. No plus minus because it is applicable only to sigma terms, right? Yeah. Okay. So now you have got this one. And the third one, last one, how you will fill? One will be up spin, other will be down spin. So Ml plus 1 minus 1, L will be plus 1 minus 1 is equal to 0. So S will be plus half for this one, minus half for this one, 0. 2s plus 1 will be 1. L is 0, so you get the sigma term. 1 is the spin multiplicity, G is again G into G, you get G. Plus, how do you get plus? Because 2s plus 1 is 1. That is why you got plus, right? Okay. Now this is done. Okay, yeah. This you can see I have just included it for your understanding that how do you get U conjugate? How do we get it? Just for understanding. Since this is not required in this question. Although, okay. So H2 minus is given. You know that H2 for the H2 the MO diagram you know. I'll not draw the MO diagram because it's not usable to draw. Yeah. So sigma G and sigma U, the bonding and the anti-bonding. You know, H2, one H atom, other H atom, they'll combine, and the bonding will comprise of 2 electrons. And since it is minus, 1 electron will be, it will occupy the anti-bonding orbital, right? Anti-bonding molecular orbital. So now L will be 0. Why? Because it is sigma. Sigma, for sigma, L is 0. Here I have written it. Where is it? I'll just show you. Yeah, for all sigma orbitals, this is 0, right? So that for that, this symbol corresponding to 0, we get the sigma, right? So that is by sigma here. How do we get? Uh, Now there is only one half electron, only one electron. So half, 2 into half plus 1 will be 2. Multiplicity will be 2. U, how do you get U? Yeah, now you have to see. G into G will be G for these two electrons. Even if you don't consider this electron, these two, that will be fine. You have to consider only the HOMO. Here the HOMO is your anti-bonding molecular orbital. Okay, but just for understanding sake, I've shown you. G into G will be G, then G into U for this electron, right? G into U will be U. So that is why we have got U here, right? Okay, now coming on to the question that was asked. You might have forgot the question, that what was the question, right? Yeah, so arrange the following diatomic term symbols of O2 that I showed you how to derive them in the increasing order of energy. These three are the term symbols. We have to arrange them. Yeah. For considering the ground state term symbol and the energy order, follow the sequence. You have to follow this sequence. Okay. Symmetry. The term symbol containing G will be most symmetric and will be of lowest energy. Spin multiplicity. In the next sequence, it will be spin multiplicity. You have to consider. The term with the highest spin multiplicity, 2s plus 1, is lowest in energy. And value of the symbol. For terms of the same multiplicity, the term with the uh, largest orbital angular momentum given by this. Yeah, this is orbital angular momentum. So, yeah, I'll read it out again. For terms of the same multiplicity, the term with the largest orbital angular momentum given by this is lowest in energy. Okay. Ground state term has the least energy. The energy order will be directly proportional to the bond length. You know this. As the energy increases, bond length also increases, bond strength decreases, bond becomes weak. As you know that if the electron goes to the anti-bonding molecular orbital, so the bond becomes weak. The energy order will be inversely proportional to bond strength and stretching frequency. Stronger is the bond, stronger will be the stretching frequency that we study in the IR, infrared spectroscopy. Okay, yeah, for this. Now you have to see for the O2 molecule, the energy order becomes, this is the energy order, sigma 3g minus. This will be the ground state term. Why this is the ground state term? Because the spin multiplicity is the highest. You can see amongst these three, this is the highest. 3 will be the highest. 3, 1 and 1 is there. So amongst these two, you can see it is sigma, pi, delta, phi. So the value of orbital angular momentum is higher for this one as compared to this. It is 2, 0, 1, 2. It is 2 here, and for sigma it is 0, right? See here. For delta we have 2, for sigma we have 0. So that is why this is of lower energy as compared to this one. So this will be your energy order. So I've written the bond strength order also for your understanding. So bond strength will be reverse. This is the energy order. So the bond strength, higher the energy, weaker will be the bond. So bond strength will be reverse. Bond length will be of the same order, right? As in, this has the highest energy, so this will be the weakest bond having the uh, like longest length, right? Then followed by this one and the last one here. And stretching frequency has the order of bond strength, right? Bond strength that you study, the stretching frequency of this term will be highest term symbol, then this and then this one, right? Okay. Yeah. So this I've just included for understanding. For H2, we get these term symbols. That what I showed you earlier, this was H2 minus. Okay, you have to see this. This was H2 minus. I just wanted to show you the term symbol. That is why I included this one. How do you derive it? But this is for H2, simple H2. Okay. So this is the energy order. These are the terms that you can like for practice sake you can practice this one how to derive for the H2. Okay. So these are the term symbols that we get. This will be the ground state term. Why? Because it is G. In the rules you can read it. The term symbol containing G will be most symmetric and will be of lowest energy. So this is G. That is why it is ground state, right? Then this will be a first excited state because it has higher spin multiplicity 3 and this one has 1, right? This has higher, so its energy is less. Okay, so yeah, this is all for this question. This is also related to the previous term symbols question itself because such questions are asked, which are allowed, which are forbidden. So you should know this. Which of the following electronic transitions are allowed? Okay. So allowed transitions between the electronic states of linear molecules are subject to the following selection rules. Linear molecules, you should know this. O2, H2, right? N2, for example. Laporte rule. So the orbital angular momentum, change in the orbital angular momentum will be equal to 0 plus minus 1, 0 or plus minus 1. Spin selection rule, delta S is equal to 0 for sigma terms only. Sigma plus to sigma plus, sigma minus to sigma minus is allowed. And if it is plus to minus, it will not be allowed. Plus to plus is allowed, minus to minus is allowed. I have given only for the allowed. Okay? Plus to plus is allowed, minus to minus is allowed. Thus, but plus to minus is not allowed, and similarly, minus to plus is not allowed. And parity selection rule is G to U is allowed. G to G will not be allowed. U to U will not be allowed. Okay. So for the first one, you can see it. First one, 1 sigma G plus to 1 sigma G plus. It is given to us. So this is not allowed. Why? Because it is G to G. I told you it should be G to U or U to G. Then it will be allowed. So this is not allowed, right? G to G. Second one is your pi to sigma. This is allowed. Why? Because delta S is 0, 2 minus 2 will be 0, and pi to sigma. For sigma we have 0, for pi we have 1, right? So, sorry, I've written this is not minus 1, this is not plus 1, this is minus 1, right? Yeah, sigma to pi. So it will be 0 minus 1, it will be minus 1. But anyway, it is allowed only because it is plus minus 1, right? Laporte rule includes that the orbital angular momentum should be either equal to plus 1 or minus 1. So it is minus 1, so it is allowed from pi to sigma. And about the third one, if we talk about this one, it is not allowed. Why? Because the spin is changing, spin multiplicity 2 to 3, right? 2 to 3. It should be 2 to 2 or 3 to 3. Here delta S is not 0, as delta S is 3 minus 2, it is 1. It is not 0. So that is why it is not allowed, right? Not allowed. Okay. So you can note down these rules. It is very important to remember that. And yeah, you can write this also that plus 2 minus or minus 2 plus for the sigma terms only rule. It is not allowed. Not allowed. Okay. Similarly, G to G and U to U is not allowed, right? You can note down this one also. This is not allowed, and I have given here only for the allowed ones. These two are not allowed, right? And similarly, when delta S is not equal to 0, that will not be allowed. Or if the orbital angular momentum is not 0 or plus minus 1. For example, if we go from sigma term to sigma pi delta term, that will not be allowed, right? Because this is 0, the orbital angular momentum 0, and this is 2, right? So 2 minus 0 will be 2. Yeah. So that doesn't follow the Laporte rule. Okay. Now, yeah, so it is done with this question as well. Okay. So coordinated water molecules of a cadmium group complex can be successively replaced by bromide, finally to result in cadmium tetra. This is a tetrahedral complex. In this process, the fourth equilibrium constant is observed to be higher than the third one because. So you have to give the reason. So thermodynamic and kinetic stability. This topic is also important. In fact, coordination whole chapter is important. You cannot miss this chapter. Okay. So equilibrium constant for the last step is always the highest. 3 molecules of H2 are released during the fourth step. The aqua cadmium 2 species is octahedral. An anion bromide replaces a neutral H2O molecule from the coordination sphere. So these are the options that you have to answer why it is the fourth one is higher than the third one. Okay. So thermodynamic stability tells us about the strength of the metal ligand bond, right? Kinetic stability is how fast it is occurring, how fast the substitution is occurring, for example. It tells us, it gives us information about the rate. But thermodynamic stability, how stable it is, how stable the bond is. It tells us about this. Okay, thermodynamic. Yeah. So you can see here the probability of replacement of H2O by ligand L decreases as the steric hindrance increases. So in general, you have to remember this. In general, Kn, it is a rate constant, Kn. Kn is greater than Kn plus 1. For example, K2 is greater than K3, right? K1 will be greater than K2. It is about the replacement of H2 by another ligand. Okay, so Kf is your formation constant. So now this is if it is a metal with the water, right? And L ligand if we add, suppose Cn minus if we are adding, in that case, that is a different case. This bromide is a different case. For Cn minus, it is seen that the trend is that I shown here. Kn is greater than Kn plus 1. That is K1 is greater than K2, which is greater than K3 and K. Okay, so K1 is highest, then it is K2, the rate, the formation constant decreases, right? Now, I'll skip that. Okay, Kf. So this is a formation constant, ml by m into L, Kf, ml. Higher the value of formation constant, more will be the stability of the complex bond. So if Kf is greater than 1, numerator is greater than denominator, this will be greater than this, means ml is greater than MH2. Ligand binds strongly with metal in comparison to the metal with water. Okay, the incoming ligand. In this case, it is bromide. You'll understand more in the next slide. You'll be wondering what is this. Yeah, so here it is. So I showed you that if we use Cn minus as a ligand, if we talk about cadmium with when cadmium is coordinated to the water molecules and when we are adding Cn minus step by step. So in that case, K1 will be greater than K2, which will be greater than K3 and K4. That will be the sequence that I was writing. Okay, that is for the Cn minus. right? K3 and K. But this question, which I have included, is an exceptional case, right? Okay. Now you can see exception here. Kn plus 1 is greater than Kn. The trend here is the same. K1 is greater than K2 is greater than K3. But here you can see that K4 is greater than K3. Now that the reason you have to give in this in the answer. In the fourth step, entropy is greater. Some unusual structural and configurational changes occur. Now, if you have this cadmium complex with water, bromide ions are adding. So first one will add, the first bromide will come and water will lose. So you can see here that two molecules, one and one, two, and here also two. Here it is two molecules. Here also there are two. Here or in the third step, two on the left side, two on the right side. But here in the fourth step, you can see there is, then we add a bromide. In the fourth step, the 3H2O molecules are released. So entropy is increasing. Here it is 4, and on the left side of the equilibrium, it is 2, right? Molecules are 2 molecules. Here it is 2 molecules. Here it is 4 molecules. So entropy is increasing, right? Randomness is increasing. Entropy is increasing. So for this reason, the K4 becomes greater than K3. This one, right? K4 becomes greater than K3. So yeah. So the answer will be 3 molecules of H2O are released during the fourth step. This will be your answer, right? Fourth equilibrium constant is observed to be higher than the third one because 3 molecules of H2O are released during the fourth step. Okay. So why you can see here that this is for additional information that the value of K1 goes on the K1, K2, K3, K4, they go on decreasing, right? Like it is 10 to the power 5.28 something. It is, I don't remember the exact value actually. So it is 5.28 something, and the next will be 4.10 to the power 4 point something. So in that way, it is decreasing. Why? Because the probability of replacement of H2O by a ligand L decreases as the steric hindrance is increasing on adding the external ligand and removing the motor molecules, right? Okay, so this one is done. Yeah. Okay. So this is a question. Assign the order of lability for the three sets of complexes. So this is these three sets are given to us. We have to tell about the lability and inertness. Yesterday also I included one question, I guess, from this topic. Okay. So these are the complexes that are given: ALF6 3 minus, SIF6 2 minus, PF6 minus, SF6. And in the set B, this is sodium complex with water, magnesium, and aluminium, strontium, calcium, magnesium. These belong to the same group, the C1. I'm talking about the C. So beryllium, magnesium, calcium, strontium, barium, right? These belong to the same group, right? So, okay, this is the answer. Lability, substitution of one or more ligand by another ligand readily. That is the lability. And inertness is inability or lesser ability of a ligand to be replaced by another ligand. That is inert. I showed you yesterday that D3 is inert, right? From DBT. And D9 complexes having JTD, D4 complexes, they are D4 high spin. They are labile, right? D9 has J3, D4 also, because it has electron in the Eg. They are labile. Okay, so inertness is directly proportional to charge by size, and lability is directly proportional to size. So for the A set, you can see that we have aluminium in the +3 oxidation state, silicon in +4, phosphorus in +5, and sulfur in the +6, right? So now you can see that as the charge is increasing, inertness is also increasing. The nuclear charge is increasing, effective nuclear charge. It will hold the water molecules tightly and will not be water, it is fluoride ions here. It will hold the fluoride tightly and it will not let it go because it has higher positive charge, right? So that it will be higher, it will be inert, the site. That is why this is the order of lability. The charge is least here, 3, and the charge is increasing in this order, right? So higher the charge, higher will be the inertness and lesser will be the lability. Inertness and lability are inversely, they have inverse relation. Okay, so talking about the B, the set B1, sodium, magnesium, aluminum. Here also it is the same thing, that on the basis of charge you can distinguish Na plus, Mg2 plus and aluminum 3 plus. Highest charge, highly inert and less labile. So PQR, PQR. This sodium will easily replace the water molecules, and magnesium will be in the middle, and aluminum will resist, okay, the replacement of H2. Substitution basically. Okay, so talking about the third one, this is a different one. Now you can see beryllium, magnesium, calcium, strontium, barium. So these belong to the same group. Going down the group, the size increases, right? So strontium has the highest size, followed by calcium, and then magnesium has the smallest size, right? So Mg2 plus has small size and the highest effective nuclear charge. It will hold the water molecules most strongly and will not let them go. So strontium has a large size and its charge is less, effective nuclear charge will, like, the electrons will spread out, right, because of the large size. So the water molecules can be replaced for the strontium, and it is calcium then. The least ability will be for the magnesium. It has small size, and small size corresponds to high charge, right? Like if we talk about the halide ions that we talk, so we say that fluorine has a small size, high electronegativity. Yeah, we say in, like, if we talk in organic, or like not specifically in organic, here also. So yeah. Anyway, so strontium, calcium, and magnesium. Magnesium has the smallest size, high charge density, has highest effective nuclear charge. It will hold the water molecules more strongly and will not undergo substitution easily, and therefore it is least labile. And strontium is most labile. Okay. Yeah. So that is all for this question. Okay. So it's done. Thank you.